To continue our discussion on Green's theorem and talk about some new concepts and also see that how does this Green theorem look like in the vector notation. Okay, and then there are going to be other statements which can be deduced from Green's theorem, so there will be a different interpretation. And so we have seen the formula that the Green's theorem basically relates the double integral of a certain function in a region over R2 to a line integral which is over the boundary of that region, isn't it? So this was the analog of fundamental theorem of calculus. So today we are going to elaborate more on this, and then at the end I will also try to tell you some physical interpretation, is because it looks too much of mathematics probably to some of you. So I'll also tell you that these things are not just for the sake of curiosity that you are studying, or just that there's a formula so you study. These things have got some real applications, and the problems itself they are motivated through real life problems. All right, so let us continue. Okay, I will begin with the mathematical definitions, and then only towards the end I will try to elaborate or interpret these things in details. Okay, so curl of a vector field. So you have a vector field, and you see all the time we take some partial derivatives and this and that. So even if I have not written down that the partial derivatives exist and so on, you have to assume that, okay, because we are talking about partial derivatives. Okay, so the curl f is given by this formula, but this formula I don't have to memorize. Okay, I'll tell you that how this formula comes about, and also that what is the easy way. So we are going to see this operation or this operator often from now on. So this is the operation which we have seen when we were discussing the gradient, but I had not called it an operator. So we will often we will refer to this del as so this is a vector operator. Okay, and it has got the partial derivatives basically. So this is called the vector differential operator. And how does one act on something? So basically the rules, if I want to take the dot product of this with something, it's going to be a formal rule. Okay, so for example, the definition of curl is actually is nothing but the formal cross product of this vector operator with the vector field. Okay, so one should not get confused that this is not really the determinant, because first row has got the vectors, second row has got the operators, and the third row has got the function. So the things do not match. It's just a formal notation to simplify things. Okay, so one has to understand that how does thing take place over here. Okay, so for example, you apply the standard rule of computing the dot product, but keep in mind that wherever you have a vector and where you have operator, so that means if I am taking this multiplication over here, that means the del over del by is acting on r. That means you are going to talk about the partial derivative of r with respect to y. Okay, so that is the understanding you have to have. So that is why I have written the formal cross product. Okay, so you just understand that the curl is basically the cross product of this operator with the vector field. Okay, and hence and then this form will automatically you will get. Okay, so this is the curl, and as I said, this has got some physical meaning. I will explain towards the end. All right, and it's easy to compute. I'll just illustrate it with an example. So you just have to compute, for example, if this is the given vector field, you compute the partial derivatives of the cross terms and put them as per the rule of the determinant. That's it. Okay, and this I will not read it, and then some of the properties which are immediate from the definition. For example, if you have got a vector field which is looking like the gradient of, or which is the gradient of a function. Okay, so what kind of the vector fields are they, and if you take the curl of that, then what you are going to get is a 0. Okay, so notice here that this is a 0 vector. Okay, curl gives you a vector quantity, so it acts on a vector field and gives you a vector. Okay, so this you have to keep in mind. And how does one do it? It's, you just have to put it in the definition. Okay, and once you compute it, what you will see that there are going to be terms which will be involving second order derivatives of f. So if you assume that second order derivatives are continuous, then you know that the cross terms, so del f by del x del y is same as del f by del y del x. So you can interchange the order of the differentiation, and if you just use that, you immediately conclude that all the components of the vector are 0, and hence the curl of gradient is 0. Okay, so this is not really a difficult thing to. So basically what you have said, that the curl of a conservative vector field is 0, and then yeah, I mean, this is precisely the corollary which we have written over here. And one also has a converse to this theorem. Okay, namely that if I have a vector field whose curl is 0, can I conclude that the given vector field is conservative? The answer is yes, and you have to work about it little bit. So you have to consider simply connected domains where you are working, and then you can talk of the converse. So curl f equal to 0 is going to tell you that the vector field is conservative. Okay, as earlier, there were some theorems whose proof we skipped. This proof also I am going to skip, but it's not really the case. Namely that when I am going to talk about the vector form of Green's theorem, you will see that the proof of this one can obtain. Okay, so even though I have skipped a proof of 1 or 2 small results, but they should be taken as small exercises, and you should complete them. Okay, yeah, all right. And then the next term which we are going to need is the divergence of a vector field. Okay, so divergence is again defined in terms of the operation. So you take a vector field, and you see that we are going to talk about the partial derivatives. So you assume that the partial derivatives exist and define this. Now you see, divergence of a vector field is a scalar quantity. There is no I, j, k over here. Okay, so this you have to keep in mind, and this is precisely the formal dot product of this vector differential operator with the vector field f. Correct? So del by del x is going to act on p, del by del y is going to act on q, and so on, isn't it? So don't worry, right now these are just mathematical definitions, some notations. As I said, towards the end I will tell you that what does the curl or divergence mean, and what they have to do with the Green's theorem. Okay, and once I have these two definitions, there are certain properties which are immediate. For example, if you take the sum of two vector fields and then take the divergence, this is basically distributive and or linear, whatever you want to call it. And similarly the curl, and you can also take a vector field and take a scalar function, multiply them, so you are going to get a new vector field. So you can talk of the divergence. So divergence is basically, because it involves the derivative, so there are going to be this Leibniz rule, and hence you are going to get two terms because there is a multiplication over here. Okay, and similarly you can talk about the curl, and notice that the divergence of f times capital F, this guy, see, f is scalar, divergence f is scalar, so this is scalar. This is a vector field, but you are taking a dot product with the gradient, so this is scalar. Okay, so immediately there is no contradiction. Okay, but be careful, if there is a mistake, you correct it. So divergence of this is given by this, and the curl, if you want to compute, curl is going to be a vector, and you see that there is going to be a vector on this side also, because the cross product is a vector and curl f is a vector, and this is just a scalar multiplication. Okay, and there are a few more properties, that if you compute the divergence of the gradient, you get the second order derivatives, and basically this is the operator which is called the Laplace operator, or the Laplacian. Okay, and this plays an important role in physics, in maths and so on. So these things they come through some natural or some real world problems. Okay, and we saw that if we compute the curl of gradient, we got 0, and similarly if you compute the divergence of curl, you are going to get 0. Okay, now you see this 0 is a scalar. because you are computing the. So I'll give you the proof of the proof of the last one. All these things are just trivial. You can write down the proof and then see that it's just easy to do it. So let us see this. All you have to do is see, this is pure computation, nothing, it doesn't really involve anything else, no trick, no new idea. So compute curl f. Okay, once you know that curl can be computed using that determinant, formal determinant notation or the formal cross product, you put it in the determinant and compute, so you get this quantity. Now you want to compute the divergence. So divergence basically take the del by del x of this, then del by del y of this, and then del over del z of this, and sum them up. So this is what you are going to get, and you will notice here that you are going to get second order derivative of all these quantities. So for example, del 2r by del x by del y. Okay, this is a positive sign here, and look for r and x and y. So there is a r here and there is x and y, and it's going to come with negative sign. Okay, the only thing is the order is interchanged, the order is different, correct? Here x and then y, this is y and then x. But if you assume that the second order partial derivatives are continuous, you can apply the theorem which says that order change is allowed, and you just see that these terms just cancel each other, so you get 0. So as I said, the proof is not difficult, you just have to write step by step, that's it. Okay, so once I have these two notations, one can put the statement of Green's theorem in the vector form. Okay, so what we had in the Green's theorem, we had a vector field in the plane, and we have a simple closed curve which is the boundary of a given domain, correct? So let us see. So this is the quantity which you saw in the Green's theorem in the right hand side, where the double integral was computed. So what is this? I can think of the vector field as a vector field in R3 and compute the curl, correct? So if you do that, you notice here that these two guys, they are just functions of x and y. So when I am going to take the del by del z, I am going to get 0, and you see this is also 0. So what I am going to get, there is not going to be any component with respect to I and j, because the column corresponding to k is basically makes them basically 0, isn't it? So all we are going to get is a term which corresponds to the k vector. Okay, so which is going to be del by del x of this, which is this, and then del by del y of p, which is this. Okay, so curl f is precisely this quantity. So if you go back to the statement of Green's theorem, then the right hand side is nothing but this. So I can rewrite that quantity in terms of curl f and the dot product with k, correct? Because this is the component function, isn't it? And this tells me that the line integral of the vector field, okay, this is the line integral of the tangential component, if you remember, isn't it? Is precisely the double integral of the kth component of curl f, isn't it? So this is how you can express your Green's theorem in terms of vector notation. And once I tell you that what is this curl doing, okay, then we will have a physical interpretation of the Green's theorem also. Okay, so yeah, I mean, this is let me just tell you that how does one so this is kind of recalling the statements which we have already discussed. So this line integral is basically the integral of the tangential component of f along the curve C, correct? So there's a picture also here. So this is your curve with positive orientation, and at each point you think of a tangent. So you are basically moving, the tangent is going to move like this. So the Green's theorem, basically what does it do? It relates the double integral of the vertical component or the kth component of the curl over the domain D, okay, so that the derivative, those del q by del x minus del p by, that is the kth component of the vertical component of the curl, okay, by in terms of the line integral of the vector field, or rather the tangential the integral of the tangential component. Okay, so now what we can do is I am going to also consider here the normal component. Okay, so for example, if I talk about the line integral along the normal component, what do I get? So this basically gives you another form or another version of Green's theorem. Okay, so what I mean, one has to first write down the equation of the normal vector here. So you know that this is the unit tangent is written like this in terms of the parameters. So if the curve is parameterized by x and y, then the unit tangent vector is basically, you look at the derivative and divide by its length, isn't it? Of course, you always assume that the things are smooth, so r prime t, you have assumed that it's non-zero, so you can divide. And what is the normal vector here? It's just going to be an orthogonal vector here, but you are considering the outward unit normal, so the normal is given by this form, isn't it? Okay, so if I'm interested in computing the line integral in the normal in the direction of unit outward normal, then you first have to compute this, and if you do that, you are going to get this. Okay, this is just the dot product of two vectors, isn't it? So the line integral of the normal component of f along the simple closed curve C is denoted like this, and this is what? This is f dot n, and then this is going to be the arc length component, isn't it? This is precisely the same thing, but here you have changed the component of which of the vector field which you are integrating out. Okay, so if you put these things here, you see that r prime t in the denominator is going to get cancelled with this. So all you get is this p by prime and q x prime. So this is in terms of the dx and dy, this is how it is written, that this is p and then this is dy and this is q and then this is dx. Okay, so you see there is a small change here. When we integrated the tangential component, we had p dx plus q dy, whereas for the normal component there is a difference over here. Okay, so but what is it? I mean this is precisely a form to which Green's theorem is applicable, isn't it? Because Green's theorem, what does it say? If you have a vector field, then p dx plus q dy, the line integral of this is certain double integral. Okay, so I have some vector field here. Now that vector field is basically minus q. Okay, so the ith component is minus q and jth component is p. So if I apply Green's theorem to this new vector field, I get this. Okay, because del q by del x, but here q is your p, and then there was a minus sign, and then this minus sign is making it plus. So basically what we get, that the line integral of the normal component of the vector field is basically this. Okay, but what is this? I mean this is precisely the divergence of the vector field. See, there is no z component here. Okay, so this is another form of Green's theorem, and it is called the divergence form of Green's theorem. Okay, so these are these are very, very important theorems. Without these theorems, a lot of things will not be understood. So of course, I mean these things you will understand, these comments you will understand only if you study a little bit further about these things, or some concepts in physics, like fluids mechanics and fluid dynamics, those kind of things. So that is where the motivation comes from. So but the idea is very beautiful, which is I'm just going to talk about. Okay, so but you keep in mind that there are two possible integrals of the vector field. One is along the tangential line, or not the tangential line, the tangential component of the vector field, or you can do the same along the normal component. Okay, and you get the two different Green's theorem. Okay, sometimes they are called first and second versions. Okay, here I am putting it divergence so that it's easy to. Okay, when you simply say Green's theorem, generally you consider the first statement, which is integral of the tangential component, but when you say second or divergence form, you mean this. Okay, so let us see that what are these formulas telling us. Of course there are I mean mathematically they are nice, but what exactly they talk about, what exactly they relate. mathematical way, as I mean in the beginning I kind of motivated that we want something which is an analog of fundamental theorem of calculus. Okay, that was of course good enough, but let me give you a little more details so that you appreciate these things more. Okay, so what happens, this curl, the idea of curl basically for a vector field, it is related with the rotation or circulation of the given field. Okay, so what you have to think of some liquid flowing. Okay, I mean on the plane, first of all, I mean you can think of it that imagine a liquid flowing, and what you want to try, I mean if you want to study the rotation or the circulation of the vector field generated by that, or I mean the velocity vector field, then the idea of curls come in. Okay, the curl comes in. Okay, and I'm going to tell you that how does it relate things. So let us take a velocity vector field of a liquid flow. Then the particles of the liquid, they tend to rotate about the axis that points in the direction of the curl. Okay, so if you think of a liquid flowing and then consider the velocity vector field, then the direction of curl basically is that where the particles they tend to rotate about the axis. Okay, and the magnitude of this curl basically it tells you that how quickly the particle are moving about that axis. Okay, so this is the importance of curl, and once we have this understanding, then these integrals also makes they have some meaning. So the line integral, so if you know, I mean if you are saying that the curl is basically is a measure that how quickly the particle moves around the axis, so when you are integrating this, because you are integrating along the tangential line, so this integral basically is also going to tell me the kind of the total circulation. Okay, we had said that this also gives you the work done. Okay, but here work done by the vector field is going to be the total circulation, and of course you always consider, I mean a simple closed curve and so on. So as I said, sometimes you will see that this is also referred to as the circulation of the vector field, the line integral. Okay, so I mean the models which try to understand it, so you imagine you take like let's say take a rectangle for example, and then you have the liquid flowing in that. Okay, and you put a small wheel at the center of that region, so that you see that how does this wheel rotate, how does this and what is what is that you can deduce, or just after doing this experiment. Okay, so what you do is you imagine that you have the boundary with the positive orientation. Okay, that means you are talking about the curve flowing in the positive direction or the counterclockwise direction. So we want to basically see that how does this wheel spin, okay, or rotate. So the greater the circulation, I mean there's a spelling mistake here, the faster the wheel moves. Of course intuitively, I mean this is how it is, but if you want to calculate certain quantities, that okay, what is going to be the total circulation, then you need to talk about these integrals, because the boundary behavior is going to determine that. Okay, so we are going to consider this small model. So let us take a small rectangle. Okay, we say that its area is del x by del y, and then think of a vector field as I said, and then we want to compute the circulation of this f along this or around this rectangle. Okay, so here is a small picture. Okay, I am considering as I said the positive orientation. So circulation along each side, if I try to compute and then sum them up, I will get the total circulation. Okay, so circulation is easy because you are talking about the tangential component of the vector field, isn't it? So the vector field is P and Q, and this is the direction of in the positive direction of I. So this is just going to be F dot I, and then the total length, correct? So because along this the length is delta x. Similarly, if you look at here, this is going to be Q times dy, And if you look at here, but you see this is this part of the curve, if you just look at it, it's minus I direction. Okay, so that is why you get a minus sign here. And similarly here, if you look at it, this is minus j direction, so you get minus q over here. Okay, so I have written here like bottom side what is the circulation, top side what is the circulation, right side and the left side. Okay, and to get the total circulation, you just sum them up. So I have not written two steps. Basically what I have done is just collect the terms which has delta y and then collect the terms which has delta x. Okay, and you see that there are these points evaluation. So what you have to do is just evaluate at the initial point of the curve. Okay, you can also do at any other point, but you know it's not going to change anything. Okay, so once you have the total circulation, if you want to find the density, you divide it by the area under consideration, and what you get, that this is the circulation density. Okay, and this is precisely the term which you wanted. So if this is the density, if you want to find out the net circulation, basically you integrate it out, correct, over the region. So this is basically telling you that this integral is nothing but the net circulation of the liquid flow along this across this, I should say, the region which you have taken. And this is precisely the line integral of the tangential field or tangential component of the vector field. Okay, so this is how you get the Green's theorem. You could just knowing that what does curl do, the idea of the curl, and basically this gives you the Green's theorem. Of course, I told you that this is over a rectangle, but then you can generalize the idea. Okay. So this quantity is precisely the curl. So when you write it down, okay, so you have to read a little bit more about these things to understand them in depth. So this says that if the curl component or the vertical component of curl, which is this for a plane vector field, is 0, or rather this is non-zero, then the paddle wheel will spin with axis k, because this is only contribution is in the kth direction, correct. And if your curl f is 0, then this vector field is called irrotational. So basically it doesn't have any tendency to rotate. Okay, so these kind of things are used in understanding the flow of some liquid or gas also probably. So but I don't really know much, that I just try to tell you that how does one motivate ourselves. This part you will not see in the book. Okay, so don't worry about it. You can try to just go through it once more and just see that what is it talking about. And let me now talk about the divergence form. Okay, this also has got some physical significance. So the divergence, as the term it says that things diverge from a point. So this is the measurement of that. Okay, so the divergence of a vector field, basically it measures the tendency of a liquid to diverge from the point. Okay, so like things moving out. Okay, so this is what we are going to talk about. So in particular, sometimes you will find these names. If the divergence is 0, then the vector field is called incompressible. I like gas, those kind of things you will. So so there is a typo here. This should have been the line integral in the with respect to the normal component. Okay, the line integral of the normal component. This happens when you copy paste things. So this is, you should think of this as f dot n ds. So this refers to the outward flux of the vector field through the simple closed curve. So as I said, things diverge. So you want to see that how the total divergence is. So that means you study the line integral of the normal component of the vector field along this or through this curve. Okay, of course with positive orientation. So let us see, this also we can compute in a similar fashion. Okay, now I want to see that how things move through these boundaries. So you again look at the bottom side. So the bottom side here, you see this is the direction of minus j, and you just look at f dot minus j, and the total length here is delta x. so this is going to get minus q, and this is the direction of plus I, so you're going to get p, and then this length is delta by. Similarly here you are going to get q dx or q delta x, and here you are going to get minus p delta y, because this is the direction of minus j. Okay, so you put them together, and just the terms of delta x and delta y you collect, and you get this. So when you take delta x and delta y to 0, you are going to get a partial derivative here and then partial derivative over here, and you precisely get this quantity. Okay, so when you see that this is the so you integrate this density, because we have divided by the area, so got the density. If you integrate this density over a region bounded by the curve, then you get the net flux, so the net flow go through the region, and which is precisely this. Okay, so this is the net flux or net flow, and this is precisely the line integral of the vector field or the tangential component of the vector field along the boundary. Okay, so this is the second form or the divergence form of Green's theorem. So these guys, these two theorems are very important, and try to work out some problems. We will have some assignment problems for this section, and now our task will be to go in R3 and try to develop the corresponding notions or the corresponding theorem for which relates the triple integral over a 3D region to a double integral which is over the boundary of that region. Okay, so that we are going to get two theorems. One is going to be the Stokes theorem, and then there will be a divergence form. Okay, so there will be another divergence theorem. So these are the two things remaining, and I will try to talk about these two things in the next week. Okay, so I stop here.